All right. Hello, everyone. Hello. So we're on. Hello. Excellent. Okay. Mic check. Mic check. Hello. How do I sound? Quality looks good. Quality looks good. All right. A little bit more lighting. Said that. We look excellent. Mic is good. Audio seems fine. Video seems fine. All right. We can now begin. Yes. So, welcome. Welcome to another edition, another episode of Introduction to Security at Tufts University. I'm Ming Chow, I'm Associate Teaching Professor. All systems ready to go. Today may be a little bit more sinister. Today is a sinister day on how to make systems all not go. Yeah, so today the big topic will be distributed denial of service attacks, DDoS, and also Scapy, the Python module to actually let you do packet manipulation. So today's topic is extremely relevant to everything that's been going on, especially over the last year, because of so many schools, institutions, companies are going remote. The number of attacks to bring down systems remotely to disrupt service, such as Zoom, and especially if you're in K to 12. Any infrastructure, anything that pertains to K to 12 education, to bring down that kind of stuff, it's happening all the time. And I know a lot of school systems have had education that their classes all disrupted because attackers are trying to bring down systems and stuff. How I want to segue into the topic of distributed denial of service is last week. So last week we covered reconnaissance, network reconnaissance, and Nmap, the network mapper. And I left off the last Thursday dealing with the stealthy type of scans. Christmas tree scan, no scan, fin scan. But there's one type of scan I did not talk about last time, and I want to do it today because it is a perfect description, perfect segue into the topic of distributed denial of service attack. One interesting type of scan that you can perform in using Nmap is called the Decoy Scan. The Decoy Scan. Now, the Decoy Scan, let's take a look at the manual from nmap.org. And it is, I'm going to paste this onto Twitch. There you go. So, one of the nice things about having an iPad in front of you, you can like copy on the Mac, put it on the iPad, so you can actually cross system. Okay, how to be stealthy. How to be stealthy in doing network reconnaissance. One of the scans that is listed to do firewall / intrusion detection, evasion, and spoofing is called the Decoy Scan. Okay? Yeah, I don't think there's anything here. Okay. Preventing precursor, preventing yada 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 yada, yada yada yada. So how do you actually do spoofing or evading firewalls? Well, here. It's the -D option, decoy. Cloak a scan with decoys. The decoy scan in Nmap is also known as a cloak scan. And if you think of the word cloak, it means trying to be hiding under invisibility. So how a decoy scan looks like this. It's Nmap with a -D flag. But then you need to specify a list of IP addresses to serve as decoys or scanners as well, followed by whoever your target is. So it is minus capital D in Nmap, and then followed by a list of decoys, list of IP addresses, and then followed by the target. Okay? So the description is causes a decoy to be scanned, which makes it appears to the remote host that the host plural you specify as decoys are scanning the target network to. That gets interesting. Thus, on the target, their intrusion detection system might report 5 to 10 IP port scans from unique IP addresses, but they won't know which IP address was scanning them and which were the innocent decoys. While this can be defeated through router path tracing, response dropping, and other mechanisms, it is generally an effective technique for hiding your IP address. Interesting. Okay, this is the important point here, is yes, I would like to almost call this as the cover your ass scan. You know, it is generally effective for hiding your IP address, but there's a lot of caveats in order to make this move, to make this work. Okay? So you specify, think of it this way. I like to call the decoy scan as something called the shell game. And actually I'm going to do one right now. So I'm going to SSH. Let me actually use the basic, there's a much larger font. So I'm going to do SSH into my Kali box here. And I am going to actually do a decoy scan. So the target I am actually going to hit on my network at home. Again, if you're following this on Twitch, you won't have the following IP addresses. Probably you won't. But I have a target running at 192.168.1.241. But I'm also going to specify a number of decoys that are 192.168.1.219, 192.168.1.10, 192.168.1.20, and 192.168.1.1, which is my router. So I have, separated by the commas, I have 1, 2, 3, 4 decoys scanning 192.168.1.241, which is a target. Now, 192.168.1.219 is, that is my current workstation right now, which is my Mac. 192.168.1.10 is a Pi-hole. 192.168.1.20 is some server, and 192.168.1.1 is my router. You don't need to control the IPs that are used as decoys, right? Okay, so I'm happy that you brought this question up. The answer is the answer to that question is no. You don't need to control the IPs being used as decoys. You don't need control of them. But this brings up a serious caveat though. Okay, while you don't need control, there's something else, which I'll mention in a few moments. So my IP address is not on this list, but it will be part of the decoy scan against 192.168.1.241. So I'm going to hit enter now. I'm going to have to enter my password. And I got my results. So I have a lot of ports open on the target 192.168.1.241. And again, from last time, 192.168.1.241 is metasploitable. It is a deliberately vulnerable virtual machine that you can practice on. So wait a minute, what is my IP address on Kali? And my IP address at Kali is 192.168.1.249. Here you go. 192.168.1.249 is the IP address of the Kali virtual machine I'm SSH'd into. But it is not part of the decoy scan list here. 192.168.1.219, no, 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 and no. So really, there's going to be 5 decoys, including myself. Well, 4 decoys, including myself. So how is this going to look like on 192.168.1.241? What is the target going to see on their end? 192.168.1.241. And that is where earlier today, before I did this exercise, I made a PCAP of what a decoy scan looks like. So here I am. This is a PCAP file called decoy.pcap. So what will it look like on the target end? What will it look like on 192.168.1.241, the target? And here is how it will look like in Wireshark. And this is where things get really, really dicey and interesting. I need to scroll down, scroll down, scroll down. So, boom, bing, right here, right here. This is where things get interesting. This is now where we start to see the decoy scan. And you can see 192.168.1.241 is the target. Okay? But what the target will see is a whole bunch of traffic coming from 192.168.1.10, 192.168.1.249, 192.168.1.1, 192.168.1.20 is also listed here too. So I have 4 decoys plus 1 actual attacker, which is a Kali VM at 192.168.1.249, all sending traffic Nmap scans against the target. And also it seems like they're all the packets are all over the place. So if I was a system administrator or a network operator or an analyst on working on the target, like looking at the traffic on the target, I will have no idea who's really the attacker here. Is it 192.168.1.1? Is it 192.168.1.10? Is it 192.168.1.20? Is it 192.168.1.1? Is it? I don't know. There's just too much traffic here. There's way too much traffic here to determine. I don't know who is actually the real attacker. And this is what a decoy scan is. Now, as part of the decoy scan, the attacker IP will be listed here, but so won't the decoys. So it's going to be really hard for that person on the other end monitoring 192.168.1.241 to even identify who in the world is the attacker. Is there a reason you can't exclude the real IP address? That's not part of the decoy scan, how it was written. But really it boils down, if you think of it this way, it's like a shell game. Like when you're playing as a kid, okay, you have a whole bunch of shells. Which one, which shell, look at which shell has a ball underneath it. That's what's really happening. So you can't exclude the real IP address, and that's not part of the specification that is written here. Okay, so you can't here it is. Oh, here it is. You can. Actually, I'm wrong. Actually, you are correct. Do you only get responses from the one containing your real IP address? Well, that's the other thing. Do you only get responses from the one containing your real IP address? So, once I get this result, these results right here, the reason why I can get this is because I would believe that, because I can finally, part of my real IP. But this gets interesting to Toadrill's point about excluding your IP. You can optionally use ME as one of the decoys to represent the position for your real IP address. If you put ME in the 6th position or later, some common port, some common port indicators such as solar attack are unlikely to show your IP address at all. If you don't use me, which I did not do, Nmap will put you in a random position. You can also use RND to generate a random, non-reserved IP address or RND to generate that number. So to Toadrill's point, you actually can quote-unquote kind of exclude the real IP, who's yourself, if you use the as ME as an option. So that is an option. So here it is. But this is the Decoy Scan has a very, very, very important caveat, and an extremely important caveat, which is the host that you use as decoys should be up and running, or else you may accidentally sync flood your targets. So that is, you must actually make sure that the decoys that you use, in this case, 192.168.1.219 is my current computer, that is my Mac. 192.168.1.10 is a Pi-hole. It's a real working server. 192.168.1.20 is another real server that I know is on. 192.168.1.1 is my router. These are all up and running IP addresses. If you're not using real IP addresses, if you're using like an IP address that is currently not up and running, let's say 192.168.1.215, that 1.15, I know that the .15 IP address is not live at all. If you're using a dead or non-existent IP address, you can accidentally bring down your target, which is not the point of reconnaissance or scanning. You don't want to accidentally kill or bring down your target. You're trying to extract as much information as possible. You're not trying to kill the target. If you're trying to kill the target, that's DDoS. That's a denial of service. Okay? Yeah, all of the all my decoys are at 192.168.168 because I'm on an internal network. These are all local IP. But if I'm going to be scanning like a real actual target on the internet, let's say like a 35.24, like some real IP address, I better make sure that the decoys I use are actually up and running as well. Kill means bring a target down. Like make the target not being able, yes, that's correct. What does kill mean? Like make the target not able to communicate with the internet? That's exactly what I mean. That's exactly it, yes. So if you kill a target so it's not being able to communicate with the internet, that's really bad. That means you brought it down. That means it won't work anymore. That's what you don't want to do when you're trying to do reconnaissance. Okay? Reconnaissance is you're trying to get as much information as possible. Why invalid? Okay, this is a great question. Can you explain why invalid IPs would cause an accidental attack? Okay. Yes, that is a great question. Because what happens is if you use decoys, this is a great question. If you use invalid IPs and you send them all to your target, what the target will try to do, remember what a target will try to do once they get an IP address. Remember the TCP handshake? Sync, ACK, and ACK? So if you use fake IP addresses or invalid IP addresses or IP addresses that are not alive, the target will try to answer every single phone call. Hello? 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 So think of it as the perfect explanation is if you use too many invalid IP addresses, it's like way too many telephone numbers trying to crank call, false telephone numbers trying to crank call you or prank call you. And you try to answer all of them. And by the end, if you try to pick up the phone, when you pick up the phone and you're picking up the phone at a whole bunch of like wrong numbers that don't even exist, you get really exhausted, right? So imagine if too many people are calling you, but at really wrong phone numbers or phone numbers that don't exist. You'll be like, hello, 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 and then you answer another phone call, hello, 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 and then another phone call is like, hello, hello, hello. Then you get really tired. Because if an IP address is dead or a dead decoy, and if you take a look at the Wireshark traffic, I mean, you take a look what the target will do. It will try to send an RST. Like, it will send an RST flag back to whoever the target is. But what happens is if the destination or the decoy or the IP address is dead, this won't go through. Hopefully that answers your question. Because the IP address must be alive in order to receive something on an RST. Then if it's not a live IP address, I mean, this can't happen. I can't send you back an RST. Because that IP address is dead or doesn't exist. So you got to make sure that the decoys that you use, such as these, are up and running. If you don't, and if they're dead IP, you can possibly, most likely, will sync flood or cause a DDoS against your target. Sync flood is a type of distributed denial of service attack. And this denial of service mean, well, what I mean, denial of service is a denial of service means you can't actually communicate with your target. You can't do it. But what does it mean by distributed denial of service? The first D in DDoS. And that means lots and lots and lots of computers or machines or devices on the network are just hammering you with so much traffic that you actually can't actually keep up and function. I mean, okay? Does the server, okay, if it doesn't go through, does the server just hang in there? Yeah, in this case, which is going to be your target. The target, if it does, the RST doesn't go through, it just hangs. Yep. Okay. So what is DDoS, really? So one of the documents I always love to share with people is Cloudflare. Now Cloudflare is a company, and they have a great description of what DDoS is. And their primary business is, fighting against security issues, and especially against distributed denial of service attacks. Okay, so what is a DDoS attack? And I said a DDoS attack is a malicious attempt to disrupt the normal traffic of a target, service, or a network by overwhelming the target or its surrounding infrastructure with just a flood of internet traffic. And if a computer is flooded with internet traffic, it's not going to work. And couple of very simple examples of DDoS are that you may see all the time in the real world is if too many people are trying to book tickets for a concert. And as of recent, a couple of real ugly examples of DDoS are way too many people are online at like an Amazon or a Best Buy or Microsoft trying to get an Xbox Series X or Series S. You see this all the time, is how many people have actually gone onto a website and try to buy a PS5 these days, and it doesn't, and you just can't even get onto the site. Another ugly example, very recent, of distributed denial of service is too many people are trying to sign up for a vaccine. Here we are in Massachusetts. I mean, this has happened all the time. When they opened up registration for people over 65 to sign up for a vaccine, no one could be able to do it because the target, in this case, that website that was a sign-up form, was just so overwhelmed with traffic. And then everyone got pissed off. Okay? So DDoS attacks achieve effectiveness by utilizing multiple compromised computer systems as sources of attack traffic. Exploited machines can include computers and other network resources such as IoT devices. Hello? The stream just stopped? No? Shouldn't. Hello? Let me see. Do you see that? Yeah, I see it. Okay. From a high level, DDoS attack is like an unexpected traffic jam clogging up the highway, preventing regular traffic from arriving at its destination. Again, think of trying to buy an Xbox, new Xbox. Think of buying a PlayStation. Think of trying to sign up for a vaccine when too many people are just online. Okay? Or, hell, you know, if too many people are trying to talk, which I don't think this is going to happen on Twitch, but yeah, I mean, there's sometimes like you can't even get onto a Twitch stream. Funny. So how does DDoS work? So how does this distributed denial of service actually works? Well, you saw one example of a DDoS attack, which was using Nmap. If you're using a decoy scan, that have a whole bunch of dead decoys, or not live decoy. That's one way. A very common way of conducting DDoS is just to have a whole bunch of compromised or exploited computers from around the world and just send a whole bunch of sync traffic to a target. But perhaps my absolute most favorite, and the one that is going on, and the one type of DDoS that's always going on, and this can be really, really, really powerful, is called an amplification DDoS. Amplification. One of the best reads and best documents is this. I absolutely love this one from Cloudflare. Time out. This is one of the best reads. Deep inside a DNS amplification DDoS attack. I mean, this stuff is extremely deadly, and is even being used up to this day. The most ugliest case was back in 2016 against Brian Krebs. So what is amplification DDoS attack means? Well, I want to go back and talk about ancient history. And let's talk about what amplification attacks are. Amplification attacks is really, the concept is the more computers that you add, the more what they call it, computers that you add to send traffic against a target, the better it is. Okay? So one of the most earliest example of an amplification attack is called the Smurf Attack. And the Smurf Attack involved using ping, or ICMP request. So how Smurf worked is, let's start with a picture first. The picture is this. So here's your victim. Okay, your victim is at 192.1, it's at 9.9.9.9. This is your victim, that's you. That's the attacker, that's the router. And these devices are all hack devices. Think of this device as like some hacked coffee maker, some hacked Windows workstation, another hacked Windows workstation, some server out there, and I don't know, maybe an Xbox or something. So how the Smurf attack would work is the attacker would send a ping request to the victim 9.9.9.9 here. But the issue is that instead of using the actual attacker's IP address as the source, okay, the source, oh, actually, so the victim is 9.9.9.9. So what the attacker will do is he will send a ping to each and every one of these devices. So the IP address of the destination of ping will be the IP address of each and every one of these devices. But the interesting thing is, the source address will be not from the attacker, but it would be spoofed or forged as the victim, 9.9.9.9. So how ping works is a very simple protocol. You would send a request and then to a device, and a device will send you a reply. But what happens if you send a ping request and they say, okay, here's a ping request, but oh yes, for the reply, just send it back to the target or to the victim at 9.9.9.9. And so all the devices will just blindly respond to ping. Okay, I got a ping request. Oh, I'm gonna send it back to, because the source address is 9.9.9.9. Boom, gonna send it back to the victim. So the ping reply will all go to the victim. So this is where the amplification attack goes. So we have 1, 2, 3, 4, 5 devices here that are sending 1, 2, 3, 4, 5 devices that are used to attack the victim. So if each and every one of these 5 devices get a ping request, the victim will receive 5 replies. If you add more devices, let's say another 5 devices to make it 10, the victim will receive 10. Have to receive 10 ping replies. And here's the definition. Here's the thing, and the documentation is this. To the network broadcast address of the router to relay ICMP to all devices behind the router. The attacker spoofs the source of the ICMP request to be the IP address of the intended victim. Since ICMP does not include a handshake, the destination or the target will have no way of verifying if the source IP is legitimate or not. The router receives the request and passes on to all the devices that sit behind it. All those devices then respond back to the ping. The attacker is able to amplify the attack by a multiple of however many devices are behind the router. Again, if you have 5 devices behind the router, then the attacker is able to amplify the attack by 5 times. See the diagram below. Smurf Attack is a thing of the past now because a lot of routers and systems actually block ping. However, that doesn't mean that the whole idea of an amplification attack is a thing of the past. In fact, you can make an amplification attack really, really deadly these days. So I want to go back into the text where it says, the attacker spoofs the source of the ICMP request to be the IP address of the intended victim. Since ICMP does not include a handshake, the destination has no way of verifying if the source IP is legitimate or not. So let me ask you all a question who is listening. Does anyone know of another protocol that does not include a handshake? I'll let you chime in on the stream. Can anyone here tell me another protocol or a protocol that does not use a handshake? So I'll give you a hint. TCP is going to be out of the question because TCP is handshake driven. Sync, ACK, and ACK. Okay. Alright. Is the attacker on the same network as the other devices or the victim, or is he external? This attacker is, it actually would depend. Sometimes it doesn't need to be on the same network. It doesn't, so just to make an assumption, the attacker may not be on the same network as the other devices. So, external. Okay, so I got an answer back. UDP. UDP is a really good answer. Really, UDP does not use a handshake at all. Okay? So UDP is the way to go. I like that. So huge hands up, huge kudos to Jenny he. Huge gold star. Okay. UDP does not use a handshake at all. Let's use that. Can you think of an application that uses UDP? And that is also open to the whole world. Does anyone know? There's an application or an application protocol that uses UDP. Anyone? Take a guess. I think the answer may surprise you. UDP, no handshake at all. Does it have to do with video and audio? No. FTP is generally is TCP. There is an application that everyone uses. You may not know it. You may not know that you may be using it right now, but there is an application that uses UDP. Not email, not OpenVPN. Streaming uses UDP generally, but maybe not the most effective one. Cooking_robot. DNS, domain names for domain name systems. Absolutely. You'll be surprised. Domain name system, DNS, also known as the yellow pages of the internet. You know, when you're trying to get an IP address for a particular domain, that actually uses UDP. No handshaking at all. Okay? So this is an opportunity now. Okay? This is an opportunity now to actually maybe to take advantage of DNS. There are two good criteria for a good amplification attack vector. One, the query can be set with a spoofed source IP address by way of a protocol like ICMP or UDP, such thank you Jenny, that does not require handshake. And two, the response to the query is significantly larger than the query itself. DNS, the domain name service, is a core ubiquitous internet platform that meets these criteria and therefore has become the largest source of amplification attacks. Yep. DNS queries are transmitted over UDP, meaning like ICMP queries used in the Smurf Attack, they are fire and forget. And there is also something else as well. And I want to bring up my terminal again. So I'm going to clear the screen in Kali. Does anyone here know how to do a DNS query on a Linux Unix-based system? What command can I use? Anyone? Anyone? What command line can I use? I can do a DNS query on the command line. Anyone? How do I do a DNS query on the command line? Anyone know? NS lookup. Let's do that. NS lookup. Let's do an NS lookup of reddit.com. Okay? By the way, before we do that, I'm going to clear the screen as man NS lookup. NS lookup query internet server name service interactive. Perfect. Perfect. So NS lookup perfect. So I'm going to do NS lookup reddit.com. So can you count how many characters are in this command right now? 1, 2, 3, 4, 5, 6, 7, 8, 9 including the space, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So I have 19 characters for to do NS lookup Reddit space reddit.com. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19 characters. Hit enter and there you go. I got my answer. So for a 19 character input, 19 characters. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 19 characters. I get this text, this response back that is much more than 19 characters. So if I do a word count right now, a character count, sorry. Character count. And this one has 227 characters. Not bad. So a 19 character command returns a 227 character response. That's a lot. And imagine, very much like the Smurf attack, you send all of this stuff back to the attacker. I think we can do better though. NSLOOKUP is actually, does it have verbose, does it have to have a verbose mode? Okay, that's, okay, thank you for bringing that up. That's what we want. We want something even more verbose. So we want to send as much garbage or many characters, we want to send as many characters as we can to the victim, so we can really take it down. There is actually a better version, a more verbose version of DNS that you can use in the command line, and that is dig. Clear the screen, man dig. Dig is a DNS lookup utility. It works very much like NSLOOKUP. And if you do dig reddit.com, so dig reddit.com, how many characters is it? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 characters. So you got 14 character command and you get this as your response. You're going to get something very similar to NSLOOKUP, but dig will actually give you this. Boom. All of this. Now that looks like a lot more than the, that looks a lot more than 227 characters. How many characters is this? 584 characters we can now send. So the more characters that we can send to the victim, the better it is. This is why dig is a little bit better. It's going to be a lot better than using NSLOOKUP. Okay? And does dig has a verbose mode? I think it does. Okay? Well, it may have it. I'm not entirely sure. For example, so here's the quote-unquote answer. For example, you can send the following tiny query where X is the IP address. Dig any, you can put in any domain that you want, and you can get back the following gigantic response. That's a lot of characters. That's a 64-byte query that resulted in a 3,223 byte response. I'm confused on how that broadcast works externally. If I'm on an internal network like yada 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 with a subnet of yada, then that subnet tells me the last portion of the available for individual addresses on the said network. Okay. If I have an external IP of your router and change the last portion and go to a different router, is it going to a different router, or is it going to go to every node of my ISP that I am on? And not go through the router, right? I'm not entirely sure. But hold on. But to answer your question, I've got something coming up for you for that one. Hold on for a second. In other words, an attacker is able to achieve a 50-time amplification over whatever traffic they can initiate to an open DNS resolver. And there are a lot of domain name servers out there, DNS servers out there in the world. Note ironically how the effectiveness of the attack based on the size of the response is made worse by the inclusion of huge DNSSEC keys, a protocol designed to make the internet system even more secure. So there's actually a whole bunch of, there's actually more here. But what you want is, you want to send all these characters to to the victim. And this is what happened to Brian Krebs back in 2016. And so Brian Krebs hit with record DDoS attack, and it was 665 gigabits of traffic per second. Akamai, the company that protects his site, they do both content delivery and also DDoS protection. They gave up. Okay, 665 gigabits of traffic per second is a lot. Okay? So here it is. The largest DDoS attack on record tend to label as a tried and true known method, better known as DNS reflection attack, which is exactly what I've been showing on, what I've been showing on paper, on the document. In such assaults, the perpetrators are able, here it is. In such assaults, the perpetrators are able to leverage unmanned DNS servers on the web to create huge traffic floods. Ideally, yada, yada, yada. So you may be wondering, how in the world can someone actually do a DDoS attack on an amplification or a reflection DDoS attack? How were attackers able to do this? Okay, here it is. And even more, he said, and here's a note, to Akamai, none of the attack methods employed in Tuesday's assault relied on amplification. Rather, many were garbage web attack methods that required a legitimate connection between the attacking host and the target, including sync flood, get flood, and post floods, yada, yada, yada. So, okay, so you may be wondering, how in the world can someone do a denial of service attack? How in the world can someone actually, pretend to be other computers out there? How can you even spoof or forge source IP address and packets? How can you do that? And this is where a tool, one of my favorite tools, come into play. There are few options that you have if you want to spoof source IP addresses or do any sort of packet manipulation, which is going to be necessary for things like denial of service attacks. And I want to now introduce you to my good old friend Scapy, or some people call it Scapy. S-C-A-P-Y, Scapy, Scapy.net. Scapy.net is for Python, namely for Python 3 now, because Python 2 is deprecated. So Scapy is a powerful interactive packet manipulation program. It is, again, Python based. You can use Scapy to forge or decode packets of a wide number of protocols, send them over the wire, capture them, match requests, replies, and much more. Scapy runs on all platforms, Linux, Windows, Mac OS. And the Scapy website is Scapy.net. You can either use the shell, the command line, or you can even write up your own Python program. Okay, so go to Scapy.net. And I want to show you an example of how do you use Scapy. So here I am on Kali. So I'm going to do Scapy. Here I am. I log in, and to create a packet, I would just do packet equals, well, to create a packet, you need to have headers. And one of the headers that you absolutely need is to have the IP header of a packet. Remember what the whole purpose of the IP header of a packet is. You have to specify the, destination address. So I can do DST equals, inside single quotes, 192.168.1.241. That's the target. So I have created a packet with IP header at the destination, DST equals 192, inside double quotes, 192.168.1.241. Now, a packet needs a lot more than that. Okay, so you have the source, you have the destination IP address, but what kind of a packet is this? And I'm going to create a very simple ping packet, or ICMP. And the way you actually create packets in Scapy is to use the slash notation. Think of this almost as the OSI model. So I want to have ICMP. Now this is a ping packet that has a destination 192.168.1.241. That's it. Pretty cool. Print packet. Okay. Let's get a warning. Calling string packet on Python 3 makes no sense. Okay. Print. What happens if I do ls packet? ls in packet actually will give you all the information about a packet. So if you actually, so you can see the destination is 192.162. So ls is a function built into Scapy that gives you all the information about a packet. So in this case, the source is 192.168.1.241. The destination is 192.168.1.241. The source is 192.168.1.249, which is the IP address of my Kali machine. And you can see all the other fields associated with this packet. To send it, you just said send. Oh, I have to be root. Okay. So let me get out of this again. Sudo Scapy. Okay. Packet equals IP. Okay. Ping packet. Okay. Send packet. Sent one packet. Sounds good. But remember in this one case here, the packet, if you don't specify the source IP address, is going to default to whatever you're using. But there is nothing preventing you from setting the source IP address on a packet in Scapy. So if I do packet equals IP src, I'm going to pretend the source is going to be 1.1.1.1. Destination equals 192.168.1.241. And I'm going to say ICMP as well too, a very simple example. If I do print ls packet, what happens? Now you can see where I did the forgery. The source IP address of this packet now looks like it's going to come from 192.168.1.1. The destination is going to be 192.168.1.241. So when I send this ping packet to 192.168.1.241, it's going to look like that it came from 192.1. It's going to look like it came from 1.1.1.1. So will it work? If I send a packet, send. Okay. So using Scapy, you can forge packets. You can actually spoof the source IP address of a packet. Okay. So now you might be really, really excited now about what you can do with packets and also Scapy. And this is where I am actually going to turn it over. I'm going to show you a video that a luminary in cybersecurity did last summer. His name is John Hammond. He gave this presentation at DEF CON at the Packet Hacking Village last summer. And I'm going to show you the first 30 minutes of the video on how to actually take down the internet with Scapy. Yeah, so we're now going to switch it over to a video. And I am going to actually show you.
Alrighty, hello everyone. Welcome. Thank you for tuning in. I appreciate you being here. This is a talk and presentation titled Take Down the Internet with Scapy. I'm presenting this as part of DEF CON 28 or DEF CON Safe Mode, and I'm here at the Packet Hacking Village. So let's dive into the presentation, but before we do, I've got to say this. I've said it before, I'm about to say it now, and I'm certainly going to say it again many, many times throughout the presentation. Thank you. Thank you for being here. Honestly, seriously, I know things are a little crazy and weird and not how we're used to them being at DEF CON, but thank you so much for being here. Thank you for tuning into this talk. Thank you for being a part of all this. I usually say this at the end, and I'm certainly going to, but now especially, I think it's really important. Just thank you. Thanks for being here. I really appreciate it. Okay. So the classic disclaimer, right? The start of every talk, that's just how it's got to start. These are my words, not my employers. I don't represent them. I'm not speaking for them, etc. This is stuff that I wanted to bring to you, me personally. Other disclaimer, don't or do try this at home, right? Anything that we talk about, anything that I showcase here, obviously it's a talk titled Take Down the Internet. Don't actually do that, or maybe do it at maybe your own small scale lab environment, etc. You can tinker with it and explore with it, but don't actually take down the internet, right? Cool. Next, your mileage may vary. I bring this up with everything that I kind of try and showcase. Look, I'm talking about it and I'm showing it to you. Maybe you'll have different results. Maybe something will work differently or strangely in the way that you do it if you do this sort of thing. I can't promise, and I don't mean to make this any written in stone gospel or anything. The stuff that comes out of this talk, it might be different for you, and your mileage may vary. Okay, last bit. We're the good guys here, right? We talk about security. We talk about cybersecurity. We break things for the sake of making them better. We hack for good. And I want you to do the same. The stuff that we're going to talk about and showcase in this presentation, maybe it's a little bit on the different side of the fence. I want to reiterate to you and kind of enforce it. Hey, hack for good. Okay, obligatory introduction, right? Who is this guy talking at you? Hello, my name is John Hammond. I'll try and run through this quickly because I know no one cares, not even me. I used to just do some stuff with the Department of Defense Cyber Crime Center and their Cyber Training Academy, and I also work with the Defense Threat Reduction Agency as a kind of a red team cyber operator. Right now, I'm working as a senior security researcher over at Huntress Labs. Again, not speaking for them. These are my words, not theirs. And in my free time, I like to play a little bit of Capture the Flag. I like to develop and create and host Capture the Flag events or competitions or exercises and training sets to try and make people better, to try and improve everyone's cybersecurity skill. On that same coin, I do produce some cheesy YouTube videos. I publish and showcase some Capture the Flag write-ups or programming tutorials, video guides, stuff like that. But that's all nerdy stuff that you don't really have to care about. Let's talk about what we're going to talk about. Kind of meta, right? So here's the agenda, the roadmap, the outline for our discussion. First, we'll lay the groundwork. We'll put down a little bit of a background, really set the scene for what we're going to be discussing. I'm going to be talking a little bit about Python, right? Python's kind of my weapon of choice, but we needed to make a distinction between Python 2 versus Python 3 and what we'll kind of be using as our vessel throughout this talk. Then I'm going to introduce Scapy, one really cool Python module or library that you can pull into your Python source code, use with your projects, your other scripts, whatever you're working on to do really cool low-level stuff with network packets, with the stuff that you would find in PCAPs if you were taking a look at it in Wireshark or TCP dump, etc. We're going to do that with Scapy inside of Python. So we'll talk about how to install it, some documentation, syntax, and use cases, etc. Then we'll get into the real meat of the conversation. We'll talk about different attacks that we could perform, and we'll kind of zoom in or zoom out as appropriate on some of these different things. The ping of death, the SYN flood, DNS attacks, BGP, etc. I do want to showcase a couple of IRL or in real life cases, right? Stuff that we've really seen out in the real world that is real. All about the stuff that we're kind of laying the foundation with here, Python, Scapy, and these network attacks when we're trying to take down the internet. We'll also discuss some of the defense and mitigation, some things that we could do, some things that we might consider when we take note of all these network attacks we're going to be looking at. Finally, I'll showcase some of the resources and references that I use to put together this conversation, this talk for you, and we'll have the boilerplate template slides, how you can contact me, and of course, I will thank you again and again. I'm really appreciative that you're here. All right, let's get into it. to get things rolling, let's lay the foundation. We're going to be talking about packets, right? We're here in the packet hacking village. We're talking about network-oriented stuff. So naturally, we're going to be talking about packets using Scapy, using Python, and we'll dive into that more. But I want to say, the title of this talk, right? The whole theme, take down the internet, that's going to be doing a lot of kind of jerk stuff. It's about obnoxious, annoying, adversarial, and disruptive attacks. So nothing like elite, super cool, 0 days, crazy like Ninja Warrior, cyber hacker stuff, but really just being mean and breaking stuff. We're trying to recklessly break stuff. I want to showcase some of this to you because I want to show you just how easy it is and how Python, just the same scripting language that's about on every Unix system, can do this stuff. And how you could do it if you really wanted to, but you shouldn't. You don't have to, right? Take down the internet, obnoxious, annoying, adversarial, and disruptive attacks. That's the background. All right, now let's talk a little bit about Python. I'm going to be using Python as the vessel for this talk, right? We want to make this a little bit of a technical talk and showcase some code, showcase some real stuff, rather than just pointing at numbers on a graph. So I want to lay the foundation again with Python. Python is a wonderful hacker's language. Yes, it's a scripting language. It's not compiled. It's read through an interpreter, but it is easy to read and easy to write. That means that it's super duper friendly. It's really easy to knock out quick testing scripts or to rapidly prototype some ideas. It's just handy and useful and has a lot of support between all the different libraries and modules and packages that you could pull into your code and do some really, really neat stuff. So there's some conversations, right? Because now we are in a new era. We are in 2020 and Python 2, the older version of Python, is dead. It's not on the table anymore. Python 2 reached end of life at the start of this year, and now Python 3 is the officially supported version. Please don't hate me for screaming about that. I just want to make sure, hey, everyone knows we're using Python 3 and you should be too. And of course, Python is part of Linux. It is typically shipped and natively kind of built into a lot of common Linux distributions. And honestly, you should be using Linux. I don't know why you wouldn't be. And because it is part of Linux, it's really, really easy to access it just from the command line. You can simply type in Python, and then you're inside of an interactive shell or interpreter to work with the Python language. I'm kind of being explicit here. I'm using Python 3 with that suffix 3 at the end. You probably will just be able to invoke it as regular Python, and maybe that would spin up Python 3 for you. But if it does, fire up Python 2. Hey, you should know better. Go fix that up and hop over to Python 3 now as the officially supported version. Python, while we could be working inside of the language within the interpreter or within that shell, oftentimes you'll likely want to create a script or file with a .py extension, maybe a shebang line, and you can invoke it and run it with Python just as an automated tool, not manually working through the interpreter or the interactive shell there. In a lot of our conversations, what we'll be discussing, I am assuming you're going to end up using this inside of a script with a .py extension, and you don't need that interactive interpreter. Okay, let's move on because you probably all already know about Python, and this is boring. So let's talk about Scapy. Scapy is incredible, fantastic, phenomenal. It is a module, it's a library, it's something you can just install, pull in to use with your Python code, and it gives you the ability to craft network packets. You can customize them, you can forge them, you can create them, you can, whatever you want, your wildest dreams, whatever sort of network layers or protocols or things that you want to use, you can get that fine-tuned, like zoomed in microscopic customization of what that packet looks like. And that's super duper cool. It's easy to install. I'm showcasing some commands here. I'm assuming, okay, a Debian-based distribution, maybe Ubuntu, you'll do a little sudo apt update and you'll install pip if you're working with that little handy Python package manager. And let's use pip install Scapy. Now, you could run Scapy in one of two ways. Very, very similar to what we talked about in Python, right? Scapy could be interactive, and you could work inside of an interpreter with a manual, like typing in commands and getting that returned back to you, like interactive shell. Or you could work with it inside of a script and have Python just import Scapy as a whole module. And you can access all of the code, the functions, the variables, all of that functionality that Scapy offers inside of your Python scripts, inside of Python. Now, this is crazy cool because we can work with TCP packets, UDP packets, any other network stuff, maybe CAN bus protocols or Bluetooth. There's so much more, and we could dive into some of the documentation for Scapy. I always want to point people to the real documentation because that's where the real stuff is, right? I'm not going to be the expert, sorry. I don't think you would call yourself the expert, and I'm not saying that to be mean. I'm just trying to say the source code is the truth, right? Documentation is the real accurate stuff. That's what's really there, really built in, and the official source, it's what's good to go to when you need help or you're trying to learn something new. Obviously, there's a man page for the command if you wanted to fire that up. Obviously, they've got an online web presence. You can check them out at scapy.net. And they have official documentation over at readthedocs.io. And of course, a GitHub page. So you can go take a look at the source code. It's open source. It's awesome. It's all Python, good stuff. The website is actually fantastic. They have a page over there called Awesome Scapy. And that will showcase other tools, exploits, and some sample code to use. And it's really, really cool. They have some good stuff on Wi-Fi, like mapping and tracking Wi-Fi networks through 802.11, making a roaming access point, performing some man-in-the-middle attacks, some Tor, onion router protocol stuff, tons and tons of great stuff. Even CVEs and exploits for common attacks, or stuff from Crack, the attack against WPA2. Super duper cool. Really recommend you go check that out. Okay, now let's talk about the basic syntax of Scapy, because if we want to use it, we have to know how to. I say that Scapy is Pythonic in that the syntax that it uses when you're working with the module, you're working with Python objects, right? The same way most everything in Python really is that you're interacting and working with an object that has methods and properties and all these attributes and things you could work with that are really under the hood, right? Functions and variables, just with a kind of a different decorated name. But being object-oriented means we can do some kind of nifty things with it. Maybe not all the time. I'm not trying to say OOP is the way. On one more common ones you'll see now is perhaps an ICMP or a ping flood. And we can certainly send other kinds of floods. One of the most common ones you might see is a SYN flood. SYN flood is another denial of service or DOS attack, which will make that server, your victim, unavailable to respond. It'll be just too busy. It'll be bogged down. It'll be hosed because something will be consumed. I did mention, though, that this ping of death attack is less common today, right? More so now, you'll see other kinds of attacks that are still this denial of service attack, right? We're being a jerk. We're overwhelming, flooding, and just bogging down the resources on that victim or target. So one of the more common ones you'll see now is perhaps an ICMP or a ping flood. And we can certainly send other kinds of floods. One of the most common ones you might see is a SYN flood. SYN flood is another denial of service or DOS attack, which will make that server, your victim, unavailable to respond. It'll be just too busy. It'll be bogged down. It'll be hosed because something will be consuming all of the available server resources. We're going to cause that by sending packets with that SYN flag set. So you know TCP packets, right? TCP being the transmission control protocol, which ensures there is a connection in place by using the three-way handshake, right? The client on one side of the conversation will send to the server a packet with the SYN flag set to synchronize or start the conversation and begin requesting communication. The server over on the other end of the conversation will say and respond back with a SYN ACK packet or a packet sent with those flags set. Finally, the client, knowing that the server has responded, that someone actually answered the phone, it will respond once more with an ACK flag set on a packet, or the acknowledgement, okay, someone is listening and we can talk, we can have this conversation. Interesting thing though, on step 2 of that process, or in the middle of the 3-way handshake communication, the server, while it sends that SYN ACK packet, it will wait to receive that ACK packet from the client so that it can begin having this conversation. So, the attack is simple. We just send a ton of SYN packets where we're just starting all these conversations. We're dialing the phone, but once someone answers, we don't care. We don't respond to them with an ACK packet. So they're overwhelmed, right? The phone keeps ringing. They're going to pick it up and they're going to want to talk to someone, but no one will be there. They're just not having this conversation, but they're still holding the phone and more are ringing. That will hog all the resources. That will cause that target victim to not be able to respond to other legitimate traffic because, okay, hey, they're busy, tied up with other stuff. All those resources are being utilized right now. Because this attack brings that server to the halfway point in the 3-way handshake, right? They've started the communication but have not responded to the server's acknowledgement. That means that it's halfway communicated. That's why it's called that half-open attack. Kind of interesting. So let's take a look at the source code, right? Scapy, again, makes this super duper easy. We're performing this attack in, realistically, 2 lines of code that could even be shortened to 1 because, hey, maybe we could abstract out that object that's not necessary for that SYN flood. We could just pass that to the function. So I'm creating the SYN flood object or variable, right? I send in a keyword argument for the destination. Again, just an IP address we'll use. We'll set an ID number for that packet and we'll specify the time to live. These values aren't extremely important for kind of just our discussion, but obviously that next layer certainly is. We create a TCP portion of this packet, and that sport, or S port is how you should read that, for our source port, that's just going to be a random ephemeral port that Scapy will help us generate with that rand short function there. That'll return something that make it look like, okay, we're coming from a different port every time. The D port, or the destination port, will be passed in as a list or a little Python array. We'll just send this over to port 80 HTTP. You could specify this to whatever you wanted to, maybe SSH or anything specifically. Specify a sequence number, specify an acknowledgement number. Again, for this example, those don't really matter all that much, but maybe they could in other scenarios. The window size, and the most important thing here, the flags that are set on this TCP packet. Obviously, I'm just passing in a string here with that capital S, and certainly enough, that stands for SYN, right? The SYN flag has been set on this packet. So we have created one packet that is just a SYN packet, the very, very first step in that TCP 3-way handshake. The next line below, we're going to end up using that SR loop function that Scapy makes available to us. And that is going to send and receive packets in a loop. So we will repeatedly, over and over and over again, send this packet. The keyword arguments there, that inter or the interval, we'll send those at 0.3 of a second. We'll retry every 2 seconds if that kind of gets dropped. And we'll have a timeout of 4 seconds. Again, those are a little extraneous, but the point that we're getting across right now is that we are looping a SYN packet being sent over and over and over again. We are flooding that target victim server with this SYN flood attack. In the case of the line of code there, we have an answered and unanswered information that's being stored as a return value of that SR loop. That'll just return a tuple, okay, or a list of what packets actually had a response and what didn't. The point that I'm trying to get across is that just these 2 lines of code are putting together this attack. And it's super duper simple. All you've done is outlined the structure. You've orchestrated this packet, and now you can put it to work. You can weaponize it as a SYN flood. You might notice, though, in this example, with this setup right here, we're sending this SYN-flood attack just with our attacker machine. One machine. So potentially, that endpoint or that target, the victim server, once it realizes, hey, I'm under attack, right? I'm in danger. If they kind of had the opportunity to look through some logs or could figure something out and determine, oh, I know the source of this attack, I can just block it off. Well, you're totally right. That's absolutely doable. For that reason, this kind of thing isn't often done just with one host, just with one attacking machine. So you bring in the conversation, okay, we're performing a denial of service attack, a DOS attack or a DOS attack. But if we had more machines in this pool, if we were attacking with multiple hosts, we could be performing a distributed denial of service attack, or that DDoS, DDoS. That might make it a little bit harder to do, harder to track down, harder to trace. However, we could do even more. We could go one step beyond that when we say our source IP address, we don't want that to look like it's coming from us. We want to hide it. We want to mask it and obfuscate that just a little bit more. But you can tell with Scapy, we are crafting our packets at the granular level. What's to stop us from specifying just that information, just the bytes, the real information that we need within that header of the packet? We could say that our source IP address comes from a different IP address, comes from a different host. We can spoof our IP address simply by passing in the keyword argument. Just as you see the example there, we specify that DST keyword argument as an IP address string. We could just as easily specify SRC, or the source IP address, and make it look like we are coming from a different location. We can spoof our IP address super easily with Scapy. And we can use that as a segue into the next attack, DNS Amplification Attacks. A DNS amplification attack is a really interesting technique that abuses the regular functionality of DNS, or the domain name system, to again overwhelm, spam, and flood a target or victim machine. The way that this works is that the attacker actually sends a legitimate regular request to a DNS name server asking for as much information as they can. So their request is a regular kind of small, tiny packet just asking for information, and the domain name server will respond with as much information as possible, and that way you get a much larger packet in response. The trick here is that with this DNS amplification attack, the attacker sets their IP address, the source, back to the actual victim or the target server that they're aiming to overwhelm and choke. You can see this here in the source code, right? We're defining, again, another object or variable to keep track of our packet. We're defining an IP header, but interestingly enough, we supply that SRC keyword value, or the source IP address of the packet that we're going to be formulating. Note, this will act as our victim. This is the target machine that will have the domain name server send back that large request. You can see again our division symbol or the / to add new layers, and we're adding a UDP packet portion, right? We'll set the D port or the destination port to 53, the default port for the domain name system or DNS servers. And what we're going to query from this DNS is anything we'd particularly like. Here, I'll just ask for anything regarding google.com or that domain. You could, of course, ask for any type or any resource record you'd like, an A record, a text record, a CNAME record. Generally, with this attack, you could expect to see the attacker request for any, as in return all of the resource records you could give me. We'll have that packet formulated, stored, and encapsulated in that DNS amp object and variable, and again, we will just send that packet along. The DNS server will respond accordingly. It will give all the information it can, but send it to that source IP address, not our actual attacker. That will flood and overwhelm, choke that target victim server. Obviously, you'd want to have more than one attack or one attacking machine doing this. You could perform this distributed denial of service, right? That DDoS. or send this request multiple times. But I think this attack is really cool and really interesting, right? If you put it in kind of layman's term or a normal human explanation, say you are at the drive-thru ordering some fast food to go or whatever the case may be. Let's say you ask the person or the teller that's chatting with you and taking your order, I want one burger or I want one drink or whatever. Typically, that job of the teller will read back your order, right? So envision this scenario. You as the driver, right? You as the attacker, you say, I want everything on the menu. And then before they can read your order back to you, you drive away and let that next person go ahead and actually hear all that information. So while you just asked for a small tiny thing and a simple, hey, give me everything you've got, the next person or your target or your victim is going to be read in a new...
Right, so we are out of time, but one thing that I'm going to stop the video, we are out of time, but one I will do is I post the link to John's talk again. Thank you so much, Sean. Give a shout out. I'll post a link to the entire video so you can actually review it on your own, see the copies, playback, or whatever. But thank you so much for tuning in. Next week we'll do crypto, and well, you may want to be interested in password cracking. See ya.